So, what is it that determines how resistive a resistor is? Well, it turns out it depends on a few different factors, and the first one is what material the resistor is made out of. And really, this gets even more complex than just, oh, well, it's made out of ceramic, or it's made out of the conductive Play-Doh stuff we were playing with, or it's more complex even than that. It turns out that for an individual material, there might be additional factors that influence how resistive it is. So there are some materials that resist more or less depending on whether it is hitting them or not. And there are some that resist more or less depending on how warm or cold they are. And so the value actually can change here. But for a given situation, for a given material, we have some value that describes how much, how resistive that the material is. And we use a rho to write this in an equation, and we call that the resistivity of the material. Again, that value might change depending on the conditions. It changes when we go from one material to another, but for a given setup, we have a material with a certain resistivity. It also depends on the geometry of the resistor. And so to understand this, let's think about our battery setup again here, where we're just going to have a battery that goes, that's linked through some device that's using the power, and then goes back to the other side of the battery. The wire here, or whatever this stuff is, that's the material that we're looking at for how resistive it is, how much resistance is being caused by that. So one thing that makes this more resistive is if we have a little tiny area for the charges to travel through, if they all get squeezed together. So it's just like if you try and get a whole bunch of people going through a single doorway all at the same time. They're all squeezed together to try and get through that doorway, and it slows everything down compared with if that doorway were gone, let's just knock down this wall that people are trying to get through. Now we have a lot bigger area to pass through, and we can travel much faster there. So the area matters. And in particular, we'll think of this as being the cross-sectional area of our resistor, or of our wire, or of any other thing that we're trying to pass electricity through. So the area matters. So the way that I have this drawn, not very consistent, this part of the wire looks like would have a little bit more resistance than this part of the wire. And so you probably have noticed that when you see power lines running along, they use really big, thick wires for that. Not just the little tiny ones that you might have, like, say, running to your headphones, but they have really, really big wires because they have a lot of energy they're trying to transport, and it's expensive to have that energy resisted. It turns out that energy turns into heat, or it turns into thermal energy by conducting as heat. And so we want to avoid that. We want to have as low a resistance as possible, so we use big, thick wires for that. The other thing that matters here is the length of the wire, or the distance that electricity has to travel through this wire or through our resistor. And so we can think about that in terms of the electric field through this. We have our positive end of the battery and our negative end here. There is some potential difference between these 2 points, between here and between here. And we know that the electric field, the average electric field, is equal to negative potential difference divided by the distance. So as our distance gets larger, our electric field gets smaller. So if we have to travel a very long distance, then there's not much of an electric field. There's a smaller force that's trying to push these electrons along, so pushing the electrons this direction, counterclockwise here. So as our wire gets longer and longer, electric field decreases. That's going to increase the resistance of our material as well, the resistance of our resistor. Now, we're talking about wires in this situation, but generally resistors are, they're little things that look about like this. where we have a wire here, and then some material in between that's doing the resisting. So the wires in circuits we typically think of as being as having a zero resistance. It's not really zero, but it's very small compared to these things that we put in there called resistors. And usually these have 4 different colored lines on them, and that helps us to understand how resistive those things are. So with these different factors, we can see that the resistance R is going to be equal to some factor that represents how resistive the material is for a given set of conditions. So that's P times the length of that resistor, or the length through which that current has to travel. So that'd be L right here, divided by the cross-sectional area A. So right here, if you looked at the side of that, we'd have kind of a circle. So our cross-sectional area A. We need to be careful about units here. Resistance is measured in ohms, like we talked about before. I also wanted to mention that ohms is usually abbreviated with the Greek letter omega, a capital omega, which is like an upside-down horseshoe. I know it's bad luck. The Greeks must not have known that. Sorry. We've also got A, the area, which is going to be in square meters. L, the length, which is going to be in meters. And then resistivity. Well, if we need to end up with units of ohms, and we're multiplying it by meters and dividing by meters squared, well, we need to have this in units of ohm meters, which is kind of a weird unit, ohm meters, but it does fit with the situation. So ohm meters times meters divided by meters squared. The meters will all cancel out, and we're left just with units of ohms for this. So that's the resistivity measured in ohm meters, and it's those 3 factors, resistivity, length, and cross-sectional area, that determine the resistance of a resistor.